I think we can start.
No, I will begin. Yes.
Yes.
On the behalf of the organization committee, I would like to thank all participants of the conference that dedicated to the to Anatoly Yakovlevich. We have remembered him as a wonderful person and brilliant scientist and the scientific advisor of the many students who are widely who known in the global scientific community. No, I if anything would like to add anything, please to say. I know that that Professor Klosov would the some words about Anatoly Yakovlevich. Yes.
Thank you very much. I'm glad to participate in the conference dedicated to Anatoly Yakovlevich Dorogovtsev as a great teacher and scientist. I had a privilege to see Anatoly Yakovlevich in action in both of these activities. I met him for the first time on his lectures on mathematical statistics delivered to students of mathematical faculty of Kiev University. It was easy for me to follow his reasoning and the proofs. Now I understand clearly that this was due to his pedagogical talent, which consists of two ingredients. This is my point of view. First, to explain any point in complicated proofs, and as well as to careful selection of statements. He is and still is one of my favorite university professors. The second time we meet with Anatoly Yakovlevich when he was a member of committee for my candidate dissertation. Prior to the procedure, I was invited to his office and explained with a lot of faults in my manuscript. Before, my estimation of my dissertation was that it's free of errors. Turns out this is not the case. However, his report on the procedure was extremely positive. So I was and still is very grateful to him for this lesson on how to behave with young people concerning the faults in their papers. There was a third occasion to cooperate with Anatoly Yakovlevich when I helped him in publishing 2 consecutive issues of his annual journal Mathematics Today. That time I learned from him how to select the mathematical topics to attract the attention of young people and how to tell them on complicated mathematical results. In general, the scientific legacy of Anatoly Yakovlevich Dorogovtsev in words for our remember, indeed. So I wish this conference great success. Thank you.
Thank you, Oleg Ivanovich. No, I think that we begin our conference. The first talk, Professor
Which are presented in the pioneer works by Schuster. He introduced the term periodogram into common usage. Yule, Fisher, Slutsky, Moran, Bartlett, and developed in numerous works by subsequent generations of mathematicians. In this presentation, we will start from fruitful article Grechka by Grechka and Dorogovtsev on parallelogram estimate asymptotic properties of the frequency and amplitude of harmonic oscillation, published about 50 years ago. In it, observed process is of the form 1-1, where with positive amplitude, we have here positive amplitude A0 and unknown frequency that belongs to some interval separated from 0, and epsilon is a strictly stationary sample continuous stochastic process defined on the probability space omega fp with 0 mean and satisfying the strong mixing condition written here. This strong mixing condition is a modification of Rosanov condition. Both imply the existence of a continuous and bounded spectral density of lambda of the process epsilon. We will use the following definition of parallelogram estimates. Definition 1-1. A parallelogram estimate of the frequency phi0 is called such frequency is determined as maximum value of this functional. We define, in turn, we define the estimate of the amplitude A0 as the value AT that is equal to square root of this functional at the point phi t. Theorem 1-1, it belongs to Professor Dorogovtsev and was published in the cited paper. Under strong mixing condition, firstly, these estimates are strongly consistent in this sense, and if the value of spectral density at the point phi0 is positive, then the properly normed vector of estimates AT and phi t is asymptotically as t tends to infinity normal n 0 R1, where covariance matrix R1 is given by the relation states that under strong mixing condition, the relation 1-4 is fulfilled. Here is a typo. Here must be written phi, the letter phi, and the result 1-4 was obtained in my PhD thesis in 1973, written under supervision of Professor Dorogovtsev. The second basic element, spectral measure of regression function. For linear regression, it was introduced in the paper by Grenander about 70 years ago. This is quite old paper. This concept allows, in some cases, to write down the covariance matrix of the limiting normal distribution of the norm statistical estimates, such as the least square estimate, parallelogram estimates, and others, of unknown regression coefficients. Later, this idea was used by many authors, including Ibragimov and Rosanov. They speak about spectral measures of regression functions in this book, Gaussian random processes. for nonlinear regression function, G considers the gradient of this function, and then the components of the matrix spectral measure mu of the gradient of the nonlinear regression function are defined from the relations 1, 1, 5. And additionally, it is assumed that the relation 1, 6 is fulfilled for the connection of the uniform and L2 norm of the derivatives of regression function. Then the properly normed estimate of the parameter theta 0 under additional conditions of regularity is asymptotically as t tends to infinity normal with limiting covariance matrix 1.7. This is 1.17. This is a kind of sandwich, so-called sandwich formula. F of lambda is the spectral density of the stationary process epsilon. Bad news, always 70 plus years of the existence of spectral measure of regression function concept, it has become clear that the class of regression functions for which these measures exist is quite narrow. Good news. This class contains functions of the form t to the power n multiplied by sine of phi t to the power n multiplied by cosine phi t. Phi belongs is a real number. These examples were mentioned by Grenander in his original article, and it helps to solve statistical problems, at least for trigonometric regression models. It is important to know that the for trigonometric regression functions, spectral measures are atomic and concentrated only at the true frequencies of harmonic oscillations. And the third basic element is a central limit theorem for stationary process satisfying strong mixing condition and weighted by the gradient of the regression function if epsilon is not Gaussian. The first result of such a kind belongs to Holivaux, obtained in 1971. The proof of this central limit theorem uses Rozanov central limit theorem for stationary processes under strong mixing condition and the concept of spectral measure of regression function. See the book of Rozanov stationary random processes. The second part of my lecture is devoted to the Professor Knopov's field generalizations of theorem 1.1. I would like to say that all the theorems are formulated in my arrangement in this lecture, and I use my own notation. In this part of the lecture, we will speak about the field generalizations of theorem 1.1 obtained by Professor Knopov with scientific support by Professor Dorogovtsev Sr. and collected in the monograph by Knopov Optimal Estimates of Stochastic Systems Parameters of 1981. Let epsilon be homogeneous sample continuous random field with zero mean, and G be a real periodic with p period 2p over all the variables function consider the problem of estimating a vector parameter phi 0 by observation of random field to 1, where we denote where this product means just a notation for such a vector. And unknown value of vector parameter theta 0 belong to the parallelepiped phi separated from 0 with positive amplitude. Example, taking g of t of such a kind, cosine of the sum of variables, we get the direct generalization of the regression function in the original Rogovtsev theorem. We are speaking about. Formulating mixing condition for random fields is significantly more complex than for stochastic processes. In section 1.6 of the book Ivanov-Leonenko Statistical Analysis of Random Fields, different strong mixing conditions for random fields are considered. And section 1.7 contains the proof of central limit theorem for random fields under strong mixing condition, associated with names of many mathematicians. We will use the definition used in the works by Leonenko and Yadrenko, and let S is subset of Rm. Sigma S be the sigma algebra generated by the random variable epsilon t when t belongs to this set T. If S and U are subsets of Rm, then we call the value dsu, defined here as a distance between the sets S and U. This is a standard definition of the distance between two sets. Definition 2.1. We will say that a random field epsilon satisfies a strong mixing condition if there exists such a function alpha of d, for which alpha of d monotonically tends to 0 as d tends to infinity, and for any sets S and U, we have the relation 2, 2. Returning to the observation model 2.1 and assuming temporarily that amplitude is equal to 1, introduce the following conditions. F1, this is a strong mixing condition of such a kind for a homogeneous random field epsilon. F2, the function g of t expands into Fourier series of this kind, where the series of Fourier coefficients of the function g of t converges absolutely. Consider further two functionals, 2.4 and 2.5, and define two estimates, phi t and phi wave t, by relations 2.6. The estimate phi wave t is parallelogram estimate in the classical sense. It would be, but it would be more accurate to call phi t a parallelogram like estimate. We speak about this functional given by formula 2,4. Parallelogram-like estimate, because strictly speaking, this functional 2,4 does not contain the parallelogram. There is no parallelogram in the definition of this estimate. So it doesn't make sense to call this estimate parallelogram-like estimate. The next theorem implements the basic element 1 of the further proofs. Theorem 2.1. All the theorems belongs to Professor Knopf. Under condition F1, we have such the uniform strong law of large numbers to 7 for usual parallelogram estimates, and if the conditions F1 and F2 are met, then this uniform strong law of large numbers is of the form 2,8. And using this theorem 2.1, we obtain the following consistency properties of estimates phi t and phi wave t. I would like to mention that this theorem 2.1 is used not only in the proofs of consistency of unknown parameters, of unknown parallelogram estimates, but in the proofs of the asymptotic normality as well. Theorem 2.2, the first statement, let the conditions F1, F2 are fulfilled, and the Fourier coefficients with indices, with all the indices equal to 1 is not equal to 0, then the parallelogram estimate of the frequencies phi t tends to 0 almost surely, as t tends to infinity. This estimate is strongly consistent in this sense. And under conditions F1, F2, and condition, such a condition, this absolute value of this Fourier coefficient C1 with all the indices that are equal to 1 is the maximum of all the rest coefficients. This is a maximum coefficients for all the coefficients that are written here. In this case, we again obtain the strong consistency of such a kind for classical parallelogram estimate F phi wave t, and this result has been proven for parallelogram-like estimate in my terminology. As for the basic element 2, for proving the asymptotic normality of the estimates phi t and phi wave t, the concept of spectral measure of regression function is extended to functions of many variables. See the cited books by Knopf and Ivanov and Leonenko. Due to complexity and generality of regression model 2.1, Professor Knopf's book does not contain the proofs of the asymptotic normality of vector estimates phi wave t and phi t. Instead, under additional conditions on the periodic function g, the coordinate-wise asymptotic normality of these estimates is proven. The proof utilizes the field central limit theorem by Leonenko of 1978, who uses strong mixing condition of the type F1. This is the basic element 3 of the proofs. And the formulation of the result obtained, unfortunately, are too bulky to reproduce them in this lecture. Therefore, we omit the exact formulation of this result. And the discussed theorems revealed, as to me, a very interesting effect associated with parallelogram-like estimates and parallelogram estimates. It may turn out that the limiting Gaussian distribution of these estimates has a non-zero expectation. I don't know another estimates with such a properties. This is the property of parallelogram and parallelogram-like estimates, the unique property. If a periodic signal is of the form 2-1, that is, there is a known amplitude A0, and the dimension of the problem is equal to 1, m is equal to 1, then to define parallelogram-like estimate of A0, it is proposed to use the expression 210. Assuming that the series in 210 converges. Similarly, for parallelogram estimate of A0, the following formula is used. A T wave is given, the estimate is given, it has such a form, like in formula 211. Both estimates are strongly consistent and asymptotically normal under conditions of asymptotic normality of phi t and phi wave t. In the paper by Professor Knopov, estimation of unknown parameter of almost periodic function in the presence of noise, some of the results described above are extended for dimension m equal to 1 to almost periodic signals, from periodic function to almost periodic signals in models with stationary noise satisfying strong mixing condition. We'll return to almost periodic signals in the next section of the lecture. Parallelogram estimates when noise is local functional of a Gaussian stationary process. Suppose the observed process is of the form 3-1, strictly speaking, is the same form as in the original paper by Professor Dorogovtsev Sr. But the process epsilon satisfies the following conditions. G1, epsilon is a local functional of Gaussian stationary process Xc of t, that is epsilon of t is equal to g of Xc of t, where g of x is a Borel function with zero mean and the process epsilon has a zero mean and the finite force moment. G2, C is a mean square continuous measurable stationary Gaussian process with zero mean. G3, the condition G3, covariance function of Xi has the form, this is so-called Bessel covariance function, has the form 3,2, that is covariance function is a convex linear combination of the functions B of such a kind, where the parameters psi are this is monotonically increase in sequence, and alpha j are positive parameters. It is assumed that phi 0 is not equal to Cj for all j from 0 to k. Phi 0, this is unknown frequency of the harmonic oscillation. Remark 3.1, if psi 0 is equal to 0 and alpha 0 belong to the interval 0, 1, then Xi is strongly dependent. In other cases, Xi is weakly dependent. Anyway, it may happen that process Xi has a singular spectral density 3 of such a kind. This is again the convex linear combination of the function that can be expressed with the help of the function of the modified Bessel functions of the second kind, with pair of orders alpha j minus 1 over 2. And the following condition will be used as an alternative to G3 in the formulations of the statements below. G3 asterisk. Covariance function of the process Xi is of the form 3.4, where LT is a monotonically non-decreasing slowly varying function, and alpha belongs to the interval 0, 1, open interval 0, 1, and the spectral density is a positive function. Theorem 3.1. If the conditions G1, G2, G3, or G3 asterisk who model 3.1 are fulfilled, then for parallelogram estimates phi t and a t, we have the relations 3, 5. That means our estimates AT and phi t are weakly consistent, because this is convergence is in probability, just in probability, not in almost surely they tends to 0. What is next? Under condition G1, the function g of x can be expanded into a Fourier series 3, 4 by Hermite polynomials HK of X, Hilbert space L2R phi x dx, where phi of x is a standard Gaussian density measure, density, the standard Gaussian density. So this is a standard Gaussian measure in such a Hilbert space. And we would like to introduce the next very important definition, 3.1. Suppose that the function g belongs to this Hilbert space, and for this function, or C1 is not equal to 0, or the first m-1 Fourier coefficient are equal to 0, and the next coefficient Cm is not equal to 0. Then the number m, the natural number n, m is called the Hermite rank of the function g, and we write m is equal to h rank g. Condition G4, or h rank is equal to 1 and alpha is greater than 1, or h rank is equal to m greater or equal than alpha, and the product m alpha is greater than 1, where alpha is the minimum of all the coefficient alpha j that enter in the definition of Bessel covariance function in the condition G3. In this case, in the case of using condition G3 asterisk, only the condition II is supposed, where alpha is a parameter of the process C of t of the covariance function B of t. This alpha is given here in the definition of this covariance function. It can be proved the following theorem. Under conditions G1, G2, G3, or G3 asterisk and G4, the normed vector of parallelogram estimates is asymptotically normal with zero mean and covariance matrix 3, 3, 5, where f asterisk phi is a convolution of order j of the process C spectral density function. Under conditions G1 and G3, we can prove uniform law of large numbers of such a kind, 3, 6. We have the uniform convergence to 0 just in mean square sense. And 3, 6 is the basic element 1 in the proofs of formulated theorems. The spectral measure of regression function, that is the basic element 2, is the same as in the first section, and any strong mixing condition is not used here due to Gaussianity of the process C, and the conditions G3, G3 asterisk, and G4 plays the role of basic element 3 in the proof of theorems 3.1 and 3.2. Consider one more observation. Model 3.7, where epsilon to be the process described above, and the function g is of the form 3.8, and this is almost periodic function with such a property. The coefficients of this expansion of this series are such that a of minus k is the conjugate to ak, as a frequency Fourier index lambda with index minus k is equal to minus lambda k, and all these Fourier indices are uniformly separated one from another. The absolute difference between them are greater than or equal to some positive number delta when L is not equal to K. Such a almost periodic function was considered in the book of Professor Dorogovtsev, Estimation Theory of Stochastic Process Parameters of 1982. First, it was considered, it seems to me that it was considered firstly in this book. If we suppose that these complex coefficients has such a form, and the series of the series of alpha k absolutely converges, then it appears that this almost periodic function in fact is a real one, and to formulate the results on consistency and asymptotic normality of the parameter A0. This is again amplitude, but the parameter phi0 here is it's better to call it as a scale parameter, and we assume that almost periodic function g meets the condition m. There exists such a number I0 such that the modules of this coefficient AI0 is strictly greater than all the rest modules of the coefficient AI when I is not equal to I0. On definition 3.1, parallelogram estimate of parameter phi0 multiplied by lambda I0 is said to be such a random variable phi t that such a relation is fulfilled, and parallelogram estimate of amplitude A0 is defined in such a way. The difference between classic definition and this definition is such that we have such a multiplier before the square root of functional Qt that depends on this unique coefficient I0. So, as it follows from definition 3.1, we can take the ratio of phi t over lambda I0 as parallelogram estimate over phi one of this scale parameter phi0. Theorem 3.3. If these conditions are fulfilled, are met for model 3.7, then AT tends in probability to A0, and T multiplied by such a difference tends in probability to 0 as T tends to infinity. It means that we can prove here just the weak consistency of the estimates. And theorem 3.4, under all the introduced conditions, the normed vector of estimates is asymptotically as T tends to infinity normal with 0 mean and covariance matrix 3.8. Formulated a little bit more complicated, but the formulated theorems transfer the results of cited at the end of section 2, Professor Knopov's paper, results for the observation model 3.1. To prove all this statement, diagram technique is used to prove the asymptotic normality, to prove the consistency and asymptotic normality. And this theorem 3.1, 3.4 continues the development of Professor Dorogovtsev Sr. results as well as previous statements. I would like to mention that instead of diagram technique, it can be used to prove the asymptotic normality of the estimates introduced in this section. It can be used the forced moment central limit theorem associated with the names of Newellert, Picatti, and Tudor. This is in fact, it was done, but I am not going to speak about such a modification of the proofs here. And the material of this section is described in detail in the following 3 works. Main of them is the last one, where all this is a big paper, a large paper, more about 30 pages, where all the technique necessary to prove these results is described in detail in this set works, in the set paper. And the fourth and the last part of my lecture, the recent generalization of the Rogovtsev results. Let M is greater or equal to 2. This is an inner product. And we consider such a field model for 1. and the random field is such that the condition C is fulfilled is a sample continuous, homogeneous Gaussian random field with zero mean and covariance function satisfying one of the assumptions. Assumptions I, epsilon is a tropic field, and with covariance function of such a kind, where L is a non-decreasing slowly varying function, L, slowly varying at infinity function L and alpha belong to the interval m minus integer part of m over 2. This is very interesting relation. We can't avoid such an assumption. With non-decreasing, slowly varying function f, and or another condition, Bt just is integrable on Rm. And if this under these conditions, we obtain the uniform strong law of large numbers for 2, and this is a basic element 1 in proofs of strong consistency and asymptotic normality of Rhodogram estimates phi t and at of unknown parameters of this model, and periodogram estimates phi t and at are defined similarly to the section 2, to the part 2 of my lecture. The proof of theorem for 1 is difficult and published in the paper Dickey Ivanov 2 years ago, just 2 years ago. Theorem 2, under condition C, we have the strong consistency of these estimates. To obtain asymptotic normality of periodogram estimates, we need the existence of spectral density of the field epsilon. Under condition C2, the spectral density f lambda exists and is a continuous bounding function on Rm. This is an obvious statement. However, C1 does not provide the existence of such a spectral density. For this reason, an additional assumption must be introduced. Assumption S, under condition C1, the random noise epsilon has a spectral density 4, where C of alpha is tau-bearing constant, and Ls is a slowly varying function. This is equivalent to the slowly varying function L of rho from the previous theorem. And this function is continuous. It is supposed that it's continuous on Rm without origin. Let the covariance function of the field epsilon satisfies S1 and its spectral density satisfies S. It is not bounded. It is not bounded. When we speak about spectral measure of regression function, basic element 2, we get it as weak limit of some family of measures. Therefore, to obtain the limit covariance matrix of periodogram estimates, spectral density must be admissible with respect to this measure in Billingsley terminology. Fortunately, it can be accurately proven that F is admissible with respect to this spectral measure of regression function. One more condition, it's not a principal condition, it's not so complicated condition, f of lambda is positive, and then in the theorem 3.4.3, we formulate the theorem on asymptotic normality of the parallelogram estimates. This is again the generalization of the initial result of Professor Drogovtsev Sr. Generalization, field generalization. Basic element 3 here consists of conditions C and S. The proofs of theorem 4.2 and 4.3 are given in the paper Ivanov, Savage, and Dickey. And this paper, it seems to me, probably this paper has been published already, but I have no information. Last, consider one more very important model of chirp signal, C.6. And again, here we can prove we have a complication of such a form. This is so-called linearly modulated signal or chirp signal. Here we can prove again all the theorem on consistency and asymptotic normality of the known parameters and of parallelogram-like estimate, because we have such a functional here. In the first section of statistics of stochastic process today, my PhD student Gladun will continue my lecture. He will speak about asymptotic properties of parallelogram-like estimates for chirp signal parameters. Thank you for your attention.
Thank you very much, Alexander Vladimirovich. What are questions to the Alexander Vladimirovich? Please.
Alexander Vladimirovich, you mentioned that you in some place you have to prove that the function f is admissible shift for the distribution of the initial process. Can you explain the reason why it is admissible? How to check this?
We take the standard definition of the weak convergence, and in this definition of measures, in this definition, the functions under the sign of integrals must be bounded and continuous. In our case, our function is continuous and it is not bounded, spectral density. And we just prove that in spite of such a situation, that this function is unbounded, we prove that this relation is fulfilled. That's all.
Okay.
Thank you.
Okay, thank you.
I think we can the next talk by Professor Andrei Dorogovtsev. No, please.
Okay, thank you very much. But before this, I expected to have a very small break to switch my tablets. So in 1 minute, I will appear again with new tablet and my presentation.
Yes. 10 minutes. Yes, да?
Demonstration. So let me begin my talk today. And let me share my screen. Here is my screen. And here is my presentation. My talk is called Stochastic Semigroups, White Noise Processes, and DNA Folding. And this is a joint work together with Irina Nishchenko. Actually, this work arises from two master students questions. One of my master students, Yuri Minialik, and he will present his talk on this conference. And another one was Daria Kalityuk, a student of Irina Nishchenko. So we considered the phenomena of coalescing Brownian motions. And the first part of my talk will be devoted to questions about coalescent phenomena in the system of Brownian particles. So, what is very well known? That if we have two independent Brownian motions on R, W1 and W2, with different starting points, then one can define the time of the first meeting. It is known that this time is finite with probability 1. Then one can define a new process. X1t equal to W1t for all t which is greater or equal than 0, and x2t which is equal to W2t when t is less than time of the first meeting, and W1t when t is greater than time of the first meeting. It occurs then that x1 and x2 are Brownian motions still, but they have an interesting property that after meeting, roughly speaking, that they move independently before meeting, then coalesce and move together. This is a picture. In the same way, one can construct a family of coalescing Brownian motions on R. One can consider the finite number of points, then use the same procedure of gluing, which I demonstrate for 2 points, and get a family of consistent distributions. In this way, one can get, at least due to Kolmogorov theorem, existence of so-called Aratia flow on the real line, which contain the continuum family of Brownian motion with the same property that any two motions are independent up to the meetings and coalesce and move together. This flow has a lot of interesting properties, and I must say that it is only one of examples of Brownian flows on the real line. What is Brownian flow on the real line? it consists of Brownian particles which keep the order. So if one particle start from the point which is less than another starting point, then they remains to be less equal during the whole time. And if they are Brownian martingales with respect to the common filtration, then one can try to describe such particles, such flows using mutual covariance functions and so on. In this way, Aratia flow or Harris-Brownian flows can be built on R. It is interesting to mention that in such flows, particles can coalesce. Even the bounded intervals turn into finite sets for finite time. For example, Aratia flow is maybe most studied and most attractive representatives of such situation. In this flow, one can easily see that for finite time, you get a finite number of points from any interval. Main reason for this is that as we already have seen, one-dimensional Brownian motion hits every point on real line. And there is no such property in case of RD, when dimension is greater or equal than 2. So, the question, is it possible to construct the flow of Brownian particles in RD in such way that the particles which occur in a short distance begin to move more or less together? So it will be an analog of the property that two Brownian motions hit one another on the real line. Then we can glue up this Brownian motion. Even on the plane in 2 dimensions, we cannot proceed in the same way. Two independent Brownian particles never meet one another. So we just can expect that they will occur on the short distance. And then why not to ask them to move more or less close, more or less together? Why I am asking this question from the point of view of applications? It is interesting that we have exactly the same phenomena in DNA folding or folding another long polymer molecules like long proteins or artificial linear polymers. So we know that starting from the very very chaotic random long curve, it goes to the very tight knot. It happens due to the following reason, which was discovered maybe in the middle of the previous century. If we have two paths of linear polymers, here this point are monomers, and these two monomers came very close one to another due to the motion. We all know that these monomers, like any particle which is placed into the surrounded media, persist something like Brownian motion due to the meetings with a lot of molecules of the media. And if they occurs to be close enough, some electric connection between them arise, and this connection keep them more or less close. Van der Waals force. Since then, our two particles, which surrounded on my picture by red, began to move together. Then another one pairs arise. It also began to be connected by van der Waals force, and etc. In this way, our initial long polymer molecule became to be tightly knotted. And it reflects in artificial polymers, it reflects so-called phase transition for polymers. Comparatively with the usual materials like metals, liquid, gases, polymers can have not 3 but 5 phases. And this existence of these phases is related heavily to the geometric shape of these long linear molecules. So this folding effect has place and is interesting from the point of view of applications. Since then, we see that the question how to organize Brownian motions which will move together after to be on the short distance is not of only mathematical interest. And now let's go to the second question. Second question also is very simple from the first point of view. Let us recall that due to the Donsker theorem, and even not to the Donsker, but it was proved more earlier than Donsker formulated general result. It is known that Brownian motion can be obtained as a scaling limit of the simple random walk. We just do appropriate normalization and get from the simple random walk the Brownian motion. I tried to reflect this on my picture. Then one can ask, why not to apply this construction to more complicated structures? For example, let us consider a family of coalescing simple random walks on the integer line. And actually, one of the initial construction of Aratia flow was exactly such. Aratia flow can be obtained as a scaling limit of coalescing random walks on Z. So we start from every point like 2 multiply on Z. And then when we meet another trajectory, we will move together. Then after appropriate scaling, we get a Aratia flow of Brownian motions on the real line, which are independent up to the meetings, then coalesce and move together. And again, the question arises, what happens under scaling with family of coalescing random walks on complicated growing structures? For example, on Ehrenfest cube of growing dimension. Let me know that, of course, this is not only my questions or our with Irina question. People studied it, but as far as I know, they studied such kind of questions on ZD. So not on Z, but on ZD. And maybe the good reference is a paper of Tom Kurtz and Peter Kotelainis, who get the negative answer from the point of view of interesting probabilistic structures, because they proved that the scaling limit will be inappropriate scaling. The scaling limit of coalescing random walks on the D is a Hertz semigroup. It is deterministic. It is Hertz semigroup. It is like Makin-Vlasov limit. It was proved near 2008, I think. So the question is the following: what we will have on the more complicated than just one-dimensional integers structure when we began to grow this structure like Ehrenfest cube, and how we can describe the answer. By the way, let me note that this question is closely related to the previous one. Namely, we just said that in RD, for D is greater or equal than 2, Brownian motions do not meet. But if we consider two independent random walks on Ehrenfest cube, which start, of course, from the general position. For example, we independently put two initial points on Ehrenfest cube. Then let us consider the dimension of the cube growing to infinity. Then it occurs that the time of the first meeting also goes to infinity very fast. Yeah? So in this case, we also cannot expect that they will meet. So we have two questions. One is how to build the Brownian motions, which in multidimensional space, which will go closely one to another with large probability after to be close first time. And another one which is related, how to describe the scaling limit of coalescing simple random walks on the for example Ehrenfest cube, but we will see that it is not only Ehrenfest cube. There are a lot of such constructions. Yeah? Okay, let us start to discuss at least partial answer on this question. So let me recall you what is white noise in Hilbert space. Let H be a real separable Hilbert space. Then white noise psi in Hilbert space is a family of jointly Gaussian centered random variables psi h such that psi h is linear with respect to h, and psi h has a normal distribution with zero mean and variance equal to the norm of h square. This is a very general object which you can often meet in very different fields of probability and random process theory. For example, in other language, psi, if H is the space of square integrative functions on some measurable space, then psi can be interpreted as a Gaussian centered random measure with independent increments in the space, and the structure measure equal to the initial measure on the space. If one can prefer to think in terms of functional analysis and in terms of random elements in Hilbert space, then one can proceed as follows. One can define the orthonormal basis and take a formal expansion of psi with respect to coordinates and say psi is simply a vector in brackets vector in H with independent standard Gaussian coordinates. It occurs that there are no such vector in infinity dimensional space. It is like cylindrical, it has like cylindrical distribution, and people from a theory of distributions Banach space say that it is a generalized random element, and it has a identity covariance operator. One can play with this white noises. For example, if you
Ari
have,
558.
excuse me? Oh, no. One can play with these white noises. For example, if you have two independent white noises and one can have the linear operator, which is continuous and has an operator norm greater or equal than 1, less or equal than 1. Then one can define a new white noise as follows, and it is closely related to Ornstein-Uhlenbeck construction. Yeah, we have renovation related to psi prime and Q related to the what we have from the past. Here, the definition of action of the linear operator, linear bounded operator on the white noise, is very simple. If as I said, if En is orthonormal basis in H, then formally psi is equal to the following sum, which does not converge. It converges only after pairing with element from H, where the coordinates are independent standard Gaussian variables. In the same way, the cylindrical Wiener process arise, and people who study stochastic differential equations in Hilbert space know this process very well. It is like a sum, again, formal sum of the Wiener standard independent one-dimensional Wiener processes multiplied on the basis element A. Now suppose why actually we are discussing cylindrical Wiener process, why we discussing white noise. One of the reasons is the following. Suppose that we have a function h, which is defined on 0 plus infinity. Take values in the space H capital, and is locally L2, so locally integrate in square. Then one can define easily such integral, like integral from 0 to t, hs dw s w capital, where w capital is this cylindrical Wiener process. And this integral is defined very easy, like even sum of Wiener integrals, if h is deterministic. But of course, h can be taken random, but adapted to the flow generated by the w, then this integral still exists as an Ito integral. And if the norm of ht is totally equal to 1, then beta t is a Wiener process again. In this way, one can think that we can construct a lot of Wiener processes using the same noise, the same cylindrical Wiener process. Let's see what happened at Fuzzer. So, how to get this function which is equal to 1 in the norm for any t? The answer is the following, and the answer actually comes from the quantum physics. We have a lot of examples in quantum physics when we have the unitary semigroup, which is acting on the initial condition. For example, Schrödinger equation give us such examples and so on. So suppose that Qt is a semigroup of unitary operators in H. And suppose that our H0 initially is taken from H such that it has measure 1. Then this integral is a standard Wiener process in R. So one can imagine how to get the dependence between different Wiener processes. One can work as follows. Of course, one can consider such a unitary semigroup that just one unit, but one can consider a lot of unitary semigroups such that they coalesce on the subspaces. So semigroup QS can be random, as I said, adapted to the flow of the W capital, and family of random semigroups can be used to construct family of Wiener processes. And again, one can expect that if we construct our semigroups in such a way that they coincides on the growing subspaces with the time, then corresponding Wiener processes will correlate more and more. It means that our particles will go parallelly. So now let us naturally go to the construction of the semigroup, stochastic semigroup. There is a lot of literature devoted to stochastic semigroups, and I must say that maybe beginning of the studies was initiated by famous papers of Anatoly Vladimirovich Skorokhod in 83, 84, two papers. Long papers devoted to stochastic semigroups, but Anatoly Vladimirovich discussed semigroups which mostly arise as a solution to linear stochastic differential equation, operator stochastic differential equation in Hilbert space. So he did not pay attention that the semigroup has unitary property, or he has a very special condition when semigroup has a representation as a solution to linear stochastic differential equation in operators. In our case, we will construct stochastic semigroups in a slightly different way. So let us see how stochastic semigroups arise in Ehrenfest model. Let us consider Xn a random walk on Ehrenfest cube. It's nothing else than Sims cube. I draw just three-dimensional cube here, and at any discrete moment of the time, with equal probability, you can go in any direction from the point where you are. But it can be such motion can be reformulated, and for us it is interesting. It is useful that at any time we have a vector xn, which consists of n capital coordinates xn1 and so on. Xn, excuse me, and small n capital. Then what happens? At any time, we randomly choose one of the coordinates and change its sign. That's all. So this is a random walk on Ehrenfest cube. It was constructed in order to understand the behavior of the particles in two boxes, because the particles which have coordinates which is equal to 1 can be considered as particles in one boxes, coordinates which is equal to -1 in another boxes, and exactly procedure which I described is related to initial Ehrenfest model. And there are also a lot of literature devoted to Ehrenfest model, and maybe one of the recent and large is Pitman paper about so-called cutoff effect. And it was proved that when we grow the number of coordinates to infinity, then the time which we need to achieve the uniform distribution, which is only one invariant for the random walk with a good accuracy, is like n capital multiplying the logarithm n, and after this we get a good estimation in what in total variation distance. But we don't need this result now. We will just propose an interpretation of this Ehrenfest motion as follows. Consider xn as a multiplication operator on the space L201. And this multiplication operator is very simply constructed. We just cut the interval 0, 1 uniformly on the small intervals of the length 1 over n, and then multiply our function from L201 on the plus or minus 1, depending on the coordinates, on the case coordinate of our random walk. And it is evident that this is a unitary operator. Also, due to construction which I described, it is evident that this an element of the stochastic semigroup of discrete semigroup
Алло?
of unitary operators.
Да.
So then,
Хорошо, сейчас выйду. Дякую.
excuse me. So then, Xn is an element of stochastic semigroup of unitary operators. Now, what we can proceed, how we can proceed further? We can consider what happened with this stochastic semigroup if we put n to the limit, n capital. N capital, this is the number of coordinates to the limit. But how to organize this limit? And the idea is following. Firstly, it was formulated, as I told, in the paper of my student Yuri Minyalik. Let us consider the following process. Let us start from the uniform distribution on -1, 1 in n power, and take lambda, which is positive and fix it. Then consider function f from C01 and consider the following process. 1 over square root of n, this a sum, very close. This sum is very common, for example, for central limit theorem, and for Gaussian free field theory in statistical mechanics, where people studied analogous limits for Eisen models and related Eisen and related models. And then it occurs that if we consider such a process, here I said how time is changed, t is greater or equal than 0, then This cross conversion in distribution to Ornstein-Uhlenbeck process with parameter 2 lambda, and here is its covariance E minus 2 lambda T minus S norm. So it is interesting because we see that our obtained semigroup is very trivial. We just have to substitute our noise with the new one. You remember in the beginning I proposed to you construction Q psi plus Q, let me say Q prime, psi prime. So in our case, this Q is just multiplication to E minus 2 lambda T, yeah? Okay, lambda T, excuse me, lambda T. So it is a very poor limit we have, a very poor limit. From other side, we have the following reformulation. Let me show you. One can add additional noise to split randomness. Take the additional epsilon k, which are independent standard Gaussian distribution. And just look at the same limit. If epsilon k are independent from our random walk xn, a discrete random semigroup, then we will have exactly the same limit. But now one can say that we discuss discrete stochastic semigroup, and it occurs that for this discrete stochastic semigroup, the process of its products with white noise. So actually, this is an action of xn onto white noise. We don't need h only like test function, yeah. Then converges to Ornstein-Uhlenbeck process. So one can see that here we have a stochastic semigroup which has a limit, poor limit, but why not? And moreover, if we want to consider several stochastic semigroup in this RNFest model, we can construct it. It is very easy. Why? Because we have those choice. You remember we discussed the choice of coordinates. We can start from independent distribution of coordinates and then begin to do common choice. Then we get the partial coalescence semigroup which coincide in one coordinates begin to be equal in the future. And then one can see that if we consider the appropriate scaling as before, then in the limit one can get family of correlated Ornstein-Uhlenbeck processes. That's all. So from this point of view, we understand the following, that maybe when we discuss the complicated structure, which has growing dimension, then it is maybe it is at least fruitful idea to consider the motion on this structure to relate it to some stochastic semigroups in one space like L201 now, and related to one Gaussian noise, and consider the appropriate scaling limit. So one can do this. Now let's consider more complicated construction of stochastic semigroup. In our case, we have previously finite number of coordinates. Let us discuss infinite number of coordinates, and let us discuss more heavy constructed semigroup based on the Arrhenius law. Firstly, let phi n be a sequence of independent Aratia flows on the real line. Consider the space L2 small L2R. What does it mean? This is a space which contains of sequence of square integral functions. So any element of this space is a sequence of square integral functions on the R. Then let us take arbitrary sequence of real numbers, arbitrary, and consider the unitary stochastic semigroup related to this sequence on L2 small. For 0, which is less or equal than s less or equal than t, define the unitary operator in our space as follows. I just described one coordinate. You remember, one coordinate is a function from L2R. So what I do? I just shift this square integral function on the increment of Aratia flow, which starts from the point, excuse me, n here, from the point an. This is n's coordinate of our sequence. That's all. In this case, we evidently have unitary operator. And what is interesting now, in this case, we construct a stochastic semigroup. In this way, we construct a stochastic semigroup of unitary operators. But if we consider two different two different parameters, A prime and A2 prime, then corresponding semigroups began coalesce on different coordinates. You remember that we have the following property of Aratia flow. Any 2 points will meet with probability 1. So if we start in n's coordinate here closely, then with good probability in positive time, we will get the same point. So we began to move together. Our n's coordinate for our two semigroups will work in the same way. This construction is similar to the spin glass construction. And from this point of view, one can expect correlation, which arises and grows up in this construction. And it occurs to be true. So let us consider the following stochastic, new type, I must say, stochastic differential equation in RD. Let H be just square integral function in RD. One can suppose that norm of H is equal to 1. It is just one of parameters of our equation. En, as before, be a orthonormal basis in L2 RD. Then suppose that J is a continuous function from RD to Rn capital. So this is a function which maps our finite dimensional space D into the space of sequences, yeah? And is continuous. In space of sequence, we, as usual, consider the distance which is related to Euclid distance in finite number of coordinates. Yeah? Let phi n k n is greater than 1, k is equal 1 to d are independent Aratia flows. Since we are working in RD, one can imagine that k, which is equal 1 to d, is related to coordinate number. So I will describe our equation only in coordinates. K's coordinate has a following differential. You see, to find differential, what we have to do? As before, you remember that when we consider the cylindrical linear process, we already have this sum. This H, E, N are just L2 coefficients, which give us convergence. But here, you have to see this point. Go back to the initial starting point and take to initial starting point of Aratia flow. Take this n coordinates as initial point and take the infinitesimal increment at the time t. Everything is good here. It is an stochastic integral because the xut by construction is measured up to the sigma field with respect to sigma field generated by phi up to the time. And in this way, you get correlated Brownian motions, which has a good property. When it becomes to be closed, these values also becomes to be closed, and with a large probability, we have the same increments. And the corresponding Brownian motions became to move more or less like neighbors. Then for any u which are starting point from RT, xut is a Brownian motion. But if xut and xvt are close enough, then with great probability they remains to be on the short distance. If now let us go to our polymers. If gamma is a polygonal line in RD, then gamma t, its image, has a folding property, exactly due to the property which we mentioned. Now, at the end of my lecture, let me show you a simulation which was done for me by my PhD student, Katerina Kustareva. And firstly, here is the behavior of the distance between 2 points in R2. We did simulation in R2. You see, the distance goes to 0, but not very fast. Even when we do the simulation, the first attempt was not very good because we just reached those higher peak in the left hand side of the picture, but it was proved that it must go to 0, but very slowly. And then let me show you the simulation of the common motion of two particles. We have we have to wait because a little bit, now you can see, because of weakness of my tablet. If we have a good computer, then simulation works much more easy. But you see these two particles from the first point of view, they persist a Brownian motion like independently. But after they became to be relatively close, see what happened. They became not travel parallel, but they began to travel closely one to another. Yes, they can do some independent things, but like a couple. You see, one can do something, another member of the couple can do something, but they are going like a couple. And finally, let me show you how the smooth random curve evolves in our flow. But I'm again sorry for the for your time that we have to wait a little bit to see how it goes because of my tablet. Yeah, it does not work very fastly. Let us wait a little bit. During this waiting, I must say that I already considered an image of the smooth curve in the Gaussian mapping with the smooth covariance, and I was able to prove. Oh, you see, here is it, and here it began to evolve, and I was able to prove that it can have arbitrary topological type with positive probability. One can estimate its complexity like the bridge number, Möbius energy. So one can estimate the complexity of the obtained node. But at those times, the model was such that the node was expanding. Here you can see that our model demonstrates exactly folding effect. You see, our long polymer began to be tightly folded. By the way, let me tell that this is a picture which is very similar to picture of DNA folding for very special creatures. Of course, human DNA is not closed curve. It is just a curve with end and with beginning and end. But for some amoeba, it is known that their DNA is closed curve is exactly a random node due to the surrounding media in the cell. Okay, so this was a simulation, and actually this is all what I wanted to say. Thank you for your attention.
Thank you, Andrei Anatольевич. What questions to Andrei Anatольевич? No.
May I ask a quick question?
Okay.
Yeah. Please.
I wonder what you think of the following alternative, which works in 2 dimensions only. Instead of Brownian particles in 2D, you can take Brownian disks,
Yes.
which coalesce when they, at the first time, they overlap. And you might object that the details will depend on the shape of the disks, their sizes, and it won't lead to a universal model. However, there is a conjecture that in the limit of large times and scales, the geometry of the disks only matters to the subleading order. To the leading order, you get a universal model. What do you think of this construction?
I have 2 comments. Maybe I will rotate my tablet for a moment in order to have good possibility. Okay, now I have 2 comments on this model. The first one, that if we have this shape, then it looks, at least from the first point of view for me, that when we consider the linear polymer, it is very good that we have these disks. But you see, we obtain the polygonal line, and I am not sure that it is very easy to get the statement, for example, as I proved for the smooth correlation of Brownian particles, that one can get the arbitrary topological shape of this thing, so that we have an arbitrary node. Yeah, I don't know. Maybe it can be done. The second one is much more I think much more difficult trouble because if we consider the following stochastic differential equation like xut is equal to integral with respect to r, it does not matter now, rd. Here we put h epsilon, xut minus p w dp dt, then one can consider, and xu0 is equal to u, one can consider the h epsilon, which looks like delta function. It approximates delta function. So h epsilon is like this one. Yeah. And then maybe but just square. Yeah. And then we will see that we get more or less exactly this model, because when we have two particles with such windows, one and other and another one, then when they are close, then they will begin to move exactly as you said. Yes, exactly as you said. So one can consider this, but you see what happened. You said that maybe when the time and this the size of the disk, so the epsilon tends to zero in upward direction. Actually, I must say that this was in dimension one exactly my construction of Aratia flow. I didn't know about Aratia flow anything at those time, and I published a paper in 2004 about such stochastic differential equation in dimension one, which and gets the Aratia flow in the limit. But as I said, Tom Kurtz and Peter Kotelenets, they considered the same equation, but when dimension is greater than 2, and they get the deterministic limit. They get like Makin-Vlasov limit for empirical measures related to these flows under epsilon tends to 0. So I think that it is a very interesting model, and one can try to check some chemical characteristics like, for example, collisions in this case, number of collisions, and so on. But when we go to the limit, I think that we will get some like Makin-Vlasov limit.
Right. And the limit is you keep time fixed and take epsilon to 0,
Yeah.
for instance. Yeah. Okay. Thank you.
Thank you, Andrei Anatольевич. No, I think that today the plenary talks are finished. The next talks will be on 6th.